The prototype sat on a steel table in the Izhmash Design Bureau, January 1974. It was not beautiful. The furniture was orange-brown polymer, a material that looked cheap against the matte black finish of the receiver. The magazine curved sharply. The front sight was a hooded post, and the muzzle brake, an angular vented cylinder, protruded aggressively from the end of the barrel. It looked unfinished. It looked utilitarian. It looked like exactly what it was, a machine engineered to solve a problem. Mikhail Kalashnikov stood across from it, his hands resting on the edge of the table. He was 64 years old. The AK-47 had made him a Soviet hero, a laureate, a name spoken in the same breath as Tupolev and Korolev. But this was not 1947. The world had changed. NATO had changed. The requirements had changed. And now the question was whether the philosophy that had worked for a quarter century could adapt to a new constraint, a smaller, faster cartridge. The 545 vise 39mm round sat beside the rifle in a small wooden crate, each cartridge noticeably slimmer than the 7.62 39mm that had defined Soviet infantry doctrine since the Great Patriotic War. The new round was lighter, faster, and generated less recoil, but it also generated less energy. The challenge was not simply to chamber a new caliber. The challenge was to maintain the Kalashnikov system's reliability while compensating for a projectile that behaved fundamentally differently in flight, on impact, and under stress. Kalashnikov picked up the rifle. It was lighter than the AKM, but not dramatically so. The balance was forward, intentional to manage muzzle rise. He pulled the charging handle. The bolt carrier slid back with the familiar metallic rasp, exposing the chamber. He released it. The spring drove the carrier forward, and the bolt rotated into battery with a solid click. No hesitation, no friction. The gas piston, the bolt lugs, the extractor, all of it inherited from the AK-47, but remachined, retoleranced, reproportioned for a round that weighed half as much and moved twice as fast. This was not a new tool. This was an evolution. And evolution in engineering is not about addition, it is about subtraction. The AK-74 had fewer parts than the AKM. The receiver was simpler to stamp. The gas block was smaller. The fire control group was unchanged. Every element that could be removed without sacrificing function had been removed. What remained was the irreducible core, a system that converted chemical energy into kinetic energy with absolute consistency. But there was one element that had no precedent in the Kalashnikov lineage: the muzzle brake. It was not an afterthought. It was the answer to the central problem of the 5.45mm cartridge: how to keep a lighter, faster projectile on target when the device cycled 15 times in 2 seconds. The brake was a physics equation made steel, and it would determine whether this design succeeded or failed. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. The directive came from the Central Committee in the autumn of 1972. The Soviet Army had been studying NATO's transition to the 5.56 45mm cartridge and the widespread adoption of the M16. Intelligence reports from Vietnam, from Middle Eastern territorial disputes, from doctrine papers circulating in Pentagon working groups, all pointed to the same conclusion: smaller, faster rounds were the future. The 7.62 39mm was powerful, but it was heavy. Personnel could carry fewer rounds. Recoil was manageable in semi-automatic fire, but punishing in full automatic. Accuracy degraded rapidly beyond 200 meters. The directive was simple: develop a successor, maintain reliability, reduce weight, increase effective range, and do it within 3 years. Kalashnikov had not asked for this. The AK-47 and its successor, the AKM, were in service across the Soviet Union, across the Warsaw Pact, across dozens of allied nations. Production lines were established. Training manuals were printed. doctrine was written around the hardware's capabilities. To replace it was not merely an engineering task, it was a logistical upheaval that would ripple across continents. But the pressure was real. NATO was iterating. The Soviets could not afford to fall behind, and so Kalashnikov returned to the drafting table not to invent but to adapt. The foundation would remain the long-stroke gas piston system. The rotating bolt would remain, the stamped receiver would remain, the simplicity would remain. What would change was everything else. The first challenge was the gas system. The 5.45mm cartridge generated different pressure curves than the 7.62mm. The gas port had to be repositioned, resized, and re-angled to ensure that the piston received the correct impulse at the correct moment in the firing cycle. Too much gas, and the bolt carrier would slam rearward with enough force to damage the receiver. Too little, and the system would fail to cycle. The tolerances were narrow, narrower than anything Kalashnikov had worked with before. The second challenge was the barrel. The 5.45mm projectile traveled at nearly 900 meters per second, faster than any round the AK platform had ever handled. The barrel had to be long enough to stabilize the projectile, but not so long that the equipment became unwieldy. The rifling had to be aggressive enough to impart spin, but not so aggressive that it wore out prematurely. And the chrome lining, essential for preventing corrosion in field conditions, had to be applied without affecting the bore's precision. The third challenge was the muzzle. The smaller round meant less mass leaving the barrel, which meant less forward momentum to counteract recoil. The device would climb, it would drift, it would scatter rounds across a target unless something redirected the gas pressure at the moment of exit. Kalashnikov had experimented with flash suppressors, compensators, and hybrid designs. None worked. The solution, when it came, was not elegant. It was asymmetrical, vented, and brutal in its simplicity, a device that bled gas laterally and downward, forcing the muzzle to stay level. It worked, but it also meant that every AK-74 would sound different, look different, and feel different than any Kalashnikov that had come before. And that was the risk. Users trusted the AK because it was familiar. Change that, and you risked breaking the bond between operator and equipment. Kalashnikov knew this, and he designed anyway. The AK-74 does not operate on innovation, it operates on inevitability. Every mechanical action is a consequence of the action that preceded it, and every component exists to ensure that consequence occurs without deviation. To understand how the hardware works is to understand how gas pressure, mass, and momentum interact within a closed system. The cycle begins when the trigger is pulled. The hammer, held under spring tension, is released. It strikes the firing pin, which protrudes through the bolt face and impacts the primer of the chambered cartridge. The primer ignites the propellant, and the resulting chemical reaction generates gas pressure that expands in all directions. Most of that pressure drives the projectile forward down the barrel. A small portion is diverted through a port drilled into the barrel, approximately halfway down its length. This diverted gas enters the gas tube and strikes the head of the piston, a steel rod rigidly attached to the bolt carrier. The piston is driven rearward with immediate violent force. Because the piston is fixed to the bolt carrier, the carrier moves rearward as well. But the bolt itself is locked into the chamber by two rotating lugs that engage corresponding recesses in the barrel extension. The bolt cannot move rearward until it is unlocked. The unlocking mechanism is elegant. The bolt carrier has a cam track milled into its interior surface. As the carrier moves rearward, a pin fixed to the bolt rides along this cam track, forcing the bolt to rotate. This rotation disengages the locking lugs from the barrel extension. Once unlocked, the bolt is free to travel rearward with the carrier. As the bolt carrier group moves rearward, several things happen simultaneously. The extractor, a spring-loaded hook on the bolt face, grips the rim of the spent casing and pulls it out of the chamber. The ejector, a fixed pin on the receiver, strikes the base of the casing as it clears the ejection port, flipping it out of the device. The recoil spring, compressed by the rearward motion of the carrier, stores energy. The hammer is cammed downward and caught by the trigger mechanism, recocking the system. At the rearmost point of travel, the bolt carrier group stops. The recoil spring, now fully compressed, begins to expand. It drives the carrier forward. The carrier strips a new cartridge from the magazine and pushes it into the chamber. As the carrier approaches its forward position, the cam track forces the bolt to rotate in the opposite direction, re-engaging the locking lugs. The system is now in battery, ready to fire again. The muzzle brake completes the system. As the projectile exits the barrel, gas follows it. The brake features expansion chambers and angled ports that redirect this gas laterally and rearward. The redirected gas generates a counterforce that pulls the muzzle downward and stabilizes it against the upward torque generated by recoil. This is not passive. It is active compensation occurring in the milliseconds between rounds. The entire cycle, from trigger pull to recocking, takes approximately 0.1 seconds. The device can fire 600 rounds per minute in automatic mode, though sustained use at this rate will overheat the barrel and degrade accuracy. The gas system is self-regulating. There is no adjustment for different ammunition or environmental conditions. The system compensates automatically by varying the amount of gas bled through the port based on pressure and temperature. This is the mechanism. It is not novel. It is not complicated. It is simply correct. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The first test firings took place in March 1974 at a military proving ground outside Izhevsk. The temperature was -12 degrees Celsius. The ground was frozen mud. The test protocol was standard. Fire 500 rounds in semi-automatic mode, inspect for wear. Fire 500 rounds in automatic mode, inspect for overheating. Submerge the hardware in ice water for 10 minutes, extract it, fire immediately, repeat until failure. The first prototype failed on round 1-247. The gas piston cracked. The metallurgy was wrong, too brittle for the thermal stress of rapid cycling. Kalashnikov ordered a redesign. The piston was remachined from a different steel alloy, heat-treated differently, and tested again. It survived 5,000 rounds before showing measurable wear. The second failure was the magazine. The polymer used in early prototypes was too flexible. Under load, the magazine lips would spread, allowing cartridges to shift out of alignment. The result was a double feed, 2 cartridges attempting to enter the chamber simultaneously, jamming the system. Kalashnikov switched to a reinforced polymer blend, stiffened the feed lips with steel inserts, and redesigned the follower spring to maintain consistent tension across the magazine's 30-round capacity. The revised magazine worked. The third failure was subtle. Testers reported that the accuracy degraded noticeably after firing 200 rounds in rapid succession. The barrel was heating unevenly, causing it to warp. The chrome lining was too thin in some areas, too thick in others, and the inconsistency was enough to shift the point of impact by several centimeters at 300 meters. Kalashnikov did not redesign the barrel. He redesigned the chrome lining process. The new protocol ensured uniform thickness across the bore's entire length. Each failure was a lesson. Each lesson was a refinement. By the summer of 1974, the AK-74 had undergone 17 documented revisions. The gas port diameter had been adjusted 4 times. The recoil spring constant had been recalculated twice. The trigger pull weight had been reduced from 4.5 kilograms to 3.8 kilograms after feedback from test participants who found the original pull too heavy for sustained accuracy. But the most significant revision involved the muzzle brake. Early versions reduced recoil effectively, but generated excessive lateral blast, gas venting sideways with enough force to affect anyone standing beside the user. This was unacceptable for hardware designed for close-quarters infantry work. Kalashnikov re-angled the ports, added internal baffles, and asymmetrically biased the venting pattern to direct more gas upward and less to the sides. The final design reduced lateral blast by 60% while maintaining the same recoil reduction. Testing continued into the winter of 1974. The device was fired in sand, in snow, in rain, in dust. It was dropped from heights of 2 meters onto concrete. It was left exposed to the elements for weeks without cleaning. It was subjected to thermal cycling, heated to 50 degrees Celsius, then plunged into ice water, then fired immediately. It survived all of it. In December 1974, the Soviet Army formally adopted the AK-74. Production began in January 1975. By the end of the decade, over 1 million units had been manufactured and distributed across Soviet forces. The design that had begun as a response to NATO's 556mm cartridge had become the new standard, and it had done so without abandoning a single principle of the Kalashnikov philosophy: simplicity, reliability, and inevitability. The question that defined the AK-74 was not how do we make it better, but how do we make it simpler? In a decade where Western design was trending toward modularity, accessory rails, and optical sights, Kalashnikov moved in the opposite direction. The AK-74 had fewer parts than the hardware it replaced. It had no adjustable gas regulator. It had no quick-change barrel. It had no mounting points for optics. It was, in every measurable way, more straightforward than the systems NATO was fielding, and yet this was not a failure of imagination. It was a deliberate, philosophical stance. Kalashnikov understood something that many engineers overlook. Complexity is a liability. Every additional part is a potential failure point. Every adjustment mechanism is a calibration that can drift. Every accessory is a dependency. The more complex a system becomes, the more fragile it becomes. And fragility in a tool meant to function in the hands of users in the coldest, hottest, wettest, and dirtiest environments on Earth is unacceptable. The AK-74's simplicity was not accidental. It was engineered. Consider the gas system. Western rifles of the era, such as the AR-15 M16 family, used direct gas systems or adjustable regulators. These designs allowed for fine-tuning based on ammunition type, barrel length, or environmental conditions. But they also required maintenance, knowledge, and tools. The AK-74's gas system was fixed. It could not be adjusted. It did not need to be adjusted. The system functioned with surplus ammunition, with new ammunition, with ammunition that had been stored improperly for decades. It functioned because the tolerances were loose enough to absorb variation. Consider the fire control group. It consisted of 8 components: a trigger, a hammer, 2 springs, and 4 pins. No complex sear disconnect. No over-travel adjustment. No trigger group modularity. The pull weight was fixed at 3.8 kilograms, heavy by competition standards, but safe and consistent for a military device. The mechanism was so simple that it could be disassembled and reassembled in under 30 seconds without tools. Consider the muzzle brake. It had no moving parts. It required no adjustment. It worked purely through geometry. Gas entered the expansion chambers, encountered the angled ports, and exited in a direction that counteracted recoil. There was no maintenance schedule, no wear inspection, no replacement interval. It was a piece of machined steel that performed a single function perfectly, indefinitely. This was the final curiosity. The AK-74 succeeded not because it did more, but because it refused to do anything that was not essential. Every feature that could be removed was removed. Every adjustment that could be fixed was fixed. Every component that could be simplified was simplified. What remained was the minimum viable system, a tool that could be handed to a user with 1 hour of training and remain operational for 20 years. Kalashnikov's design philosophy was rooted in his experience. He had been a tank mechanic during the Great Patriotic War. He had seen equipment fail in the field, not because of adversarial action, but because of mud, cold, fatigue, and user error. He had seen personnel struggle with hardware that was too delicate, too complicated, too dependent on perfect conditions. And he had internalized a single lesson: the best system is the one that never fails. The AK-74 embodied that lesson. It was not the most accurate, it was not the most modular, it was not the most ergonomic, but it was the most reliable. And in military doctrine, reliability is not a feature. It is the foundation upon which every other capability rests. The AK-74 remained in frontline service with Soviet and later Russian forces for over 4 decades. It served in Afghanistan, in Chechnya, in Syria, and in dozens of regional conflicts. It was licensed and produced in Bulgaria, Romania, Poland, and East Germany. It was copied, modified, and adapted by organizations that valued function over form. And through all of that, the core design remained unchanged. The gas system, the bolt, the fire control group, all of it identical to the design Kalashnikov finalized in 1974. This longevity is rare in industrial design. Most military hardware is replaced within 20 years as new technologies, new materials, and new doctrines emerge. The AK-74 endured because it was not designed to be the best. It was designed to be sufficient. And sufficiency in engineering is often more valuable than excellence. The hardware's influence extended beyond its direct service. The 5.45's 39mm cartridge became the standard for Soviet and Russian forces, influencing the development of support equipment and even export variants chambered in NATO calibers. The muzzle brake design was studied and adapted by engineers worldwide. The philosophy of simplicity, of reducing a system to its essential elements, became a reference point in discussions of military procurement and design economics. But the deeper legacy is philosophical. The AK-74 represents a moment when an engineer looked at the trajectory of technological development and chose to move in the opposite direction. While contemporaries were adding complexity, Kalashnikov was subtracting it. While others were pursuing modularity and customization, he was pursuing universality and standardization. And while the industry was embracing the idea that more features meant better performance, Kalashnikov was proving that fewer features could mean greater reliability. This was not stubbornness, it was clarity. Kalashnikov understood that the end users were not technicians or competitive shooters. They were conscripts, often with limited education, serving in conditions that ranged from Arctic tundra to Central Asian deserts. They did not need a device that could do everything. They needed a tool that would do one thing every time, without fail. The AK-74 was that tool. The final measure of the system's success is not in its technical specifications. It is not in its rate of fire, its muzzle velocity, or its effective range. It is in the fact that 50 years after its adoption, the AK-74 is still in service. It is still being manufactured. It is still trusted. And it is still teaching engineers a lesson that is too often forgotten. Complexity is easy. Simplicity is hard. And simplicity that works is the highest form of design. Mikhail Kalashnikov passed away in 2013 at the age of 94. The AK-74 remains. It remains not because it was perfect, but because it was complete. It solved the problem it was designed to solve, and it did so with the minimum number of parts, the minimum number of steps, and the minimum number of dependencies. It is a piece of hardware, yes, but it is also a lesson in what engineering can achieve when it refuses to be anything more than necessary. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching. Would you like me to translate another engineering history script following these safety and naturalization guidelines?